My name is Jacob Dahlgren, and I designed the steering system for the RC Baja. One of the most important aspects was the coordination with the rest of the team members, including the steering system with the rest of the vehicle. So I basically had to wait until the frame and the suspension were designed before I could design my system, because I had to know exactly how much space would be available. Because the frame features an impact absorbing spring system, I had to mount the entire system on the moving end of the frame, which left little room to work with. After brainstorming, I talked with Sean, who was the designer of the suspension, and we decided it would be a good idea if we used the suspension mount to mount the servo as well. This paved the way for the rack and pinion design. The requirements for the steering system were the steering angle must achieve 45 degrees, it must fully steer in less than 1 second, and it must be able to complete the RC Baja competition without failing. To achieve the steering angle of 45 degrees, I first calculated the linear distance that the rack would have to move to push or pull the steering linkages to achieve 45 degrees. From there, I calculated the diameter that the pinion would need to achieve that distance. After finding the required pinion diameter, I drew the pinion in SolidWorks and I designed a rack that would mesh with it. To keep the rack in place, I designed channels that would hold the rack while fitting into the designated space allowed for the steering system. To optimize the steering system, I soldered resistors into the wiring of the servo. This allowed me to achieve a rotation of 145 degrees from the original 90 degrees that the servo would travel. This also allowed me to use a much smaller pinion, which would help prevent damage. To reduce friction and improve manufacturability, I changed the design of my channels to a 2-piece design instead of a 1-piece. This helped reduce friction and help make the steering system as responsive as it is. So it was my intentions to design a steering system that would be really easy and inexpensive to manufacture. The rack and pinion, which were the most complex components of the system, were 3D printed. The channels were machined on a vertical mill using 5/8" square aluminum. The aluminum for the channels cost $3 and it took me 4 hours to machine. The tie rods were made using custom length threaded rod, and the tie rod ends were bought from the hobby shop. The total cost for the tie rods were $12. The most time-consuming part of the manufacturing process was assembling the steering system to the rest of the car. One problem that we came across was that the steering linkage interfered with the control arms, not allowing to get the maximum angle possible. To resolve this, we shaved down the inside corners of the control arms, and that freed up enough room to achieve the maximum angle. The steering angle was tested using the system as shown in the picture, in the top picture there. The steering angle was found to be 43 degrees. The steering system speed was tested using a stopwatch, and those times were averaged so it would improve the accuracy of the test. The steering system speed was found to be 0.407 seconds. The RC Baja car was able to perform the entire competition without failure, so I consider that a success. And here's a video of me testing the system. Overall, the project cost $187 and took 176 hours to complete. and I would consider it a success.
I'm Andy Battles, and I did the drivetrain of the RC Baja Wildcat car. For my design, I set some design requirements before I started actually designing the drivetrain. And one of them was to meet the ASME specs for the competition. The whole drivetrain also needed to be compact, and the top speed needed to be between 20 and 25 miles per hour. The total budget that I estimated was no more than $250. I actually went over by quite a lot because I didn't expect to buy all the little stuff like the electronic speed controller, the batteries, and all that. So it's actually around $450. And the total time that it took me to complete this was about 215 hours. This is a drawing of the first assembly of the drivetrain. It changed a lot throughout, but that was the general idea that I wanted. And before designing the gears in SolidWorks, I used this Excel spreadsheet, and I was able to use the RPMs of the motor to determine the pinion size and how many teeth, as well as the gear, to get the outcome of 20 to 25 miles per hour. For manufacturing, I use the SolidWorks to design all the gears, and then I use this 3D printer to print the gears. And here is a picture of them printing, and they print the base and then whatever the gear or whatever you're printing on top. Here's another one. This is the first set of gears I printed. As you can see, there's some holes right along the edges where the teeth meet the center of the gear, and this actually caused the gears to fail because the material that we use in our printer, the diameter of the actual material coming out of the machine while it's printing, it wasn't small enough to print this precise of teeth, and so it caused that little gap. Here is the gears that I designed in the gearbox. We were at the hobby shop one day talking to the hobby guy and trying to decide what kind of mount we were going to mount the gears on. And he actually pulled this gearbox out, and my gears fit perfectly, so we were able to use this gearbox. When we mounted the gearbox onto the frame, there was a little bit of interference with showing suspension mounts, and so we had to mount the gearbox onto a platform so that it could clear the suspension mounts. Here's a picture of one of the gears that failed. Those two top gears are actually both failed, and I tried multiple ways of printing, redesigning. I even contacted the company to see if there's a way we could fix this, and we couldn't find a solution. For testing, I was able to get the specs for the material that we use in our 3D printer, and I took the tensile strength that they had on their specs and was able to find the force for a round test specimen and a flat test specimen. And I found that the round test specimen took about 628 pounds of force, and the flat was 320. I was able to use the inch-strong tensile tester, and you just put your specimens into the tensile specimen, or excuse me, the tester, and the computer automatically pulls it apart once you start the test. And then it prints, or it gives these graphs. And from my calculated data compared to this data, the material was about the same, and so that it should have been fine. But I think the reason it failed was because of the small holes around the outside.